Hi, welcome to this webinar. My name is Thomas, and this is Leon.
Hi.
And we are applications engineers at the MPS office for Barcelona. Today we come to you from the MPS Now Lab, which we've created to help solve any problems that you may have with our technology. And today we're going to talk about LLC converters. More specifically, 600 watt ATX high efficiency power supply unit for PCs. So let's move on to the presentation. Besides Udiol and myself, we're accompanied today by Nicholas and Florian, who are field applications engineers for France Iberia and France Belgium. They will also be available for answering your questions during and at the end of the webinar. So let's have a look at what we're going to talk about today. Well, first we're going to go over the LLC converters applications and the motivation behind using this converter topology. Then we're going to go into understanding the LLC converter's basic operation before delving into the specific design constraints that these converters have, such as the gain, the load, the frequency, and the inductance. Then we're going to show you the tool we've developed to help you design your converter and offer you a live demonstration of how these converters work in the lab. So LLC resonant converters are switch mode DC-DC power converters that are often used in high power, high efficiency applications. The reason for this is that LLC converters offer high switching frequencies and lower switching losses. This makes them ideal for high power applications where efficiency is key, such as high quality power supplies for gaming and PCs, and high power battery charging for applications such as electric vehicles. MPS currently offers several LLC controllers, the newest of which is the HR1210 family, which will be discussed during this presentation. Designers can choose any of these controllers depending on applications and cost performance requirements. After explaining the details of the LLC converter's operation, we're going to discuss a real design case, such as the 600 watt PSU with efficiency above 90%, and multiple outputs to serve different supply voltage levels for different loads. What makes LLC converters so attractive for an application like this is that LLC converters are fully resonant, and therefore they produce less EMI. They also allow soft switching in both the primary and the secondary. We have 0 volt switching in MOSFETs and 0 current switching in the diodes. And the range at which they can provide this soft switching is very wide, which means that the efficiency is not lost at light loads. Furthermore, there's no inductor at the output, which means that all the inductors can be more easily integrated into a single magnetic structure, and this saves area and cost. And finally, as I said before, because of their low losses, LLC converters are suitable for a wide range of applications up to very high power. However, they also have some drawbacks. They are harder to design and control, and they have no fixed frequency control. But we will go into these problems further in the presentation and show you how you can solve them using MPS technology. Now let's go into understanding how the LLC converters work. An LLC converter is made up of 4 blocks. First, there are the power switches, which convert the input DC voltage into a high frequency square wave. They can be implemented either in a half bridge or a full bridge topology, depending on the application. Then the resonant tank filters the input square wave and eliminates the harmonics, outputting a sine wave of the fundamental frequency. This sine wave goes into that transformer, which is responsible for scaling the voltage down to an appropriate level through its scaling ratio, N, and isolating the input and the output of the converter. Finally, we have a rectifier, which converts the reduced sine wave back into a DC signal. The total gain of the circuit, therefore, is defined by the transformer and the resonant tank gain. As mentioned previously, the power switches can be implemented either in a half bridge or a full bridge topology. The main difference is that the full bridge topology generates a square wave with no DC offset and an amplitude of the input voltage, whereas the half bridge topology emits a square wave that is offset by half the value of the input voltage, and therefore the amplitude is going to be half the amplitude of that of a full bridge wave. Now, Having fewer transistors, the half bridge is cheaper, but fewer transistors also means more current flowing through each of them, so each of the transistors. This increases conduction loss, and in the full bridge, the current is divided over more transistors, but the changes in voltage are higher, so this results in increased switching losses. The resonant tank is made up of a capacitor and two inductors, called the resonant inductor in series and the magnetizing inductor in parallel. Its role, as I said before, is filtering out the harmonics of the square wave. Now, the tank's gain response is dependent on three parameters: the load, which is expressed through the quality factor, Q; the normalized frequency, which is the ratio between the switching frequency of the MOSFET and the tank's resonant frequency; and the normalized inductance, which is defined as the relationship between the resonant and magnetizing inductors. It's important to mention that these calculations have been made using the first harmonic analysis. This is applicable in this case because of the resonant tank's filtering behavior, which only leaves the resonant frequency at the output, and this greatly simplifies these equations. So you may be asking yourself why there are two inductors in this converter. This is understood best by observing the tank's response to heavy and light loads, depending on the inductor that is present in the circuit. With only the series inductor, there is a clear resonant peak at the tank's resonant frequency for the heavy load, but the light load has a much larger bandwidth. On the other hand, with only the magnetizing inductor, the heavy load does not peak, and the light load has a very large gain, a large gain at the magnetizing resonant frequency. Now, by joining both inductors, we obtain a frequency response that will adequately respond to a larger range of loads. And this will enable stable control for both large and small loads. So now we're going to move on to analyzing how these three parameters, the load, the frequency, and the inductor, affect the converter's operation. To begin with, we're going to focus on the gain. As I said previously, the converter's gain is the addition of two blocks: the resonant tank and the transformer. The resonant tank's gain is variable, depending on the load, the frequency, and the inductance, and the transformer's is fixed and depends on the ratio between the primary and secondary coils. Ideally, the tank should not amplify or dampen the signal. It should simply filter out the harmonics, and the transformer should be the only responsible element for changing the voltage level. Therefore, the nominal gain of the tank has to be 1. However, there are bound to be variations in the input voltage. And because the transformer's gain is fixed, as I said before, in order to obtain a constant output voltage, the tank is going to have to compensate for these changes. Therefore, when the input voltage is below the nominal value, the tank will have to slightly amplify the signal, producing the maximum resonant gain. If the input voltage is above the nominal value, then the minimum gain will ensure that the voltage at the primary of the transformer remains at the nominal value. Next up is the load, expressed through the quality factor, Q. As the load increases, the peak gain of the resonant tank will also be reduced. This means that we have to ensure that the worst case scenario, which is the overload, still meets the maximum gain requirement. The gain of the circuit can be controlled through changes in the switching frequency of the MOSFETs. Looking at the graph, you can see that there are two distinct regions. On the right, we have the inductive region, where zero voltage switching takes place. In this region, the relationship between gain and frequency tells us that as we reduce the frequency, the gain will increase, as you can see in this animation. However, this only holds until we reach the capacitive region, which is at the maximum peak gain. Then, in the capacitive region, as we reduce the frequency, the gain is also reduced. So, sorry, where was I? Yes. So the reason why we want to maintain in the inductive region is that if we maintain the inductive region, we can maintain a stable control loop for the entire system. And also, if we enter the capacitive region, we could risk shoot-through currents that could damage the MOSFETs or, at the very least, reduce efficiency. Now, as we mentioned before, different loads generate different frequency responses with different maximum gain frequencies. Now, to establish our minimum switching frequency, we must consider the worst possible case, where the load is at its heaviest. Now, if the load is light, then we're in the inductive region. However, if suddenly we were to switch a load into the overload case, we would find ourselves in the capacitive region, which is something we do not want to find ourselves in. Therefore, we have to increase the minimum frequency to where we stay in the inductive region for all loads, as you can see. Thus, we establish the following stable region. Once we've fixed the minimum frequency, let's take a look at the frequency range the converter can operate in. The maximum frequency is going to be limited by the maximum switching frequency of both the MOSFETs and the controller. But the switching frequency window doesn't have to be this large. Instead, we can define it by using the maximum and minimum gains that we established before, as you can see here. So now, finally, let's talk about inductors. If we plot the gain response of an LLC tank for a series of loads, we obtain the following graph. Now, if we trace a line joining the maximum gain points of these curves, and then we plot the same graphs for different values of the inductance, we're going to see a set of curves starting to form. If we do the same process for more values of inductance, we will arrive at the following graph. This graph shows us that for the same load, the difference between the maximum gain that the tank can reach depends on the value of the inductor. Smaller inductor will provide high gains for a wider range of loads, and this will offer us a wider range of operation. But a smaller inductor will mean higher magnetizing currents and therefore lower efficiency. So there is another trade-off to keep in mind. Now, what limits do we have for choosing our inductor? Well, we've got to consider our worst cases. First, we've got to consider that our load is at its heaviest. And now, with this heaviest load, we've got to make sure that we select our inductor so that we can still deliver enough gain to compensate for any shortcomings in the input voltage. So as you can see, designing an LLC converter is no easy task. There are many parameters, they're all correlated, and many design decisions that you make affect the rest of parameters, meaning that there are numerous trade-offs to take into account. Now, I'm going to let Uriol tell you about some of the tools we've developed to help you in this design process.
Okay, so to make this design process easier, MPS has developed a web-based tool that integrates all the calculation we have exposed previously. This is very useful because it allows the user to observe how modifying different parameters affect the design curves. To better show you how the design tool works, we are going to use one of our reference design, a 600 watts ATX power supply, which has 3 different output voltage levels, 12, 5, and 3.3. This is the block diagram for this application. It includes a back-end PFC, which increases the power factor and step up the boost voltage. Then the LLC converter reduces the voltage down to 12 volts for one output, and then 2 more back converters step down the voltage even further to 3.3 and 5 volts. In parallel, a flyback converter delivers auxiliary supply to the board and 5 volts to the standby output. For now, we are going to focus on the LLC design, which is the topic of this webinar. So this reference design is based on the HR1213. It is a combo controller that integrates a PFC and LLC control circuit together, also with the gate drivers. This device comes in different packages, SOIC20 for low-cost applications and TSOP20 for more compact ones. The regulation of the PFC and LLC is based on digital control, which gives the converter added flexibility. The user can configure and monitor the control parameters through a UART communication interface. So to make this even easier, we have created this graphical user interface where you can easily interact with the converter main parameters. First, in the configuration menu, you can set up the converter with the general specification. And secondly, in the monitor menu, you can observe real-time values for voltage and current. So coming back to the tool, the first parameter to consider for our LLC design is the input voltage. The input voltage of the LLC converter comes from the boost PFC. So therefore, our nominal input voltage will be 380 volts. But the ripple of the bus can drive the input from 360 to 410. Regarding the output voltage, the LLC is going to be delivering this 12 volts, and the current can be up to 55 amps, taking into account both the 12 volts output and also the input current for the DC to DC converters. Also, finally, the tool we can configure an overload situation. For example, in this case, we use 10%. So now we can go to the tool available in our website and start designing our converter. So once we open the design tool, the first step is to make sure our input and output parameters are correct. To make this demonstration quicker, we have already placed the previously described values in the designer. Once we begin the design process, the tool recommends us a value for the transformer tune ratio, but keep in mind that the LLC peak gain can be adjusted with different parameters. Next, we have to choose a value for the normalized inductance and the quality factor for these curves, which are the same as we saw in the presentation. Any point above the red line, which is the required max gain, will comply with the specification. Once we select an operating point, a new graph will show the gain frequency response. And also a recommended value for resonant inductor and the capacitor. This is where the LLC design tool becomes very useful, because you can see how the responses changes for different values just by clicking in the graph. At this point, the recommended values of Ln are between 4 and 8, and regarding the quality factor between 0.3 and 5. But take into account that these values may vary depending on your specifications and your designs. In our reference design, we have used an Ln of 7 and a Q of 0.5. Then you can modify the resonant inductor and the capacitor values that the tool provides to fit a normalized ones, and then observe how these variations affect the resonance frequency and the gain response. And so finally, you can move the sliders to select the operating frequency window. But remember that the minimum frequency is defined by the peak gain of the overload curve. To make sure that the system stays in the inductive region, the maximum gain can be above the frequency of the minimum required gain. So finally, by pressing this button, you can observe your results. So for today's demonstration, we will be using this board, which is the 600 watts ATX reference design. Below, you can see a two-stage common mode filter. This will help us to reduce both radiated and conducted emissions. At the top, we have the PFC structure, which will shape the input current as a sine wave in phase with the grid voltage. In this way, the power factor and the harmonic contents is improved. At the right, we have the LLC stage with the resonant capacitor and inductance and also the transformer configured with the tool. And finally, at the bottom, we have the DC to DC port with the two back converters. So this is the schematic of the LLC, and highlighted are the spots that we are sensing in this demonstration. In this way, we want to show you the soft switching effect of the half-bridge structure. First, we have the switch node voltage, which is the input of the resonant tank. Secondly, we have the current flowing through the resonant capacitor. And finally, there is the gate source voltage of the low side MOSFET. So, welcome back again to the MPS Now Lab. Here we can help you with your reference design, and we have all the tools required to analyze our reference design. So today, for this demonstration, we have a electronic load, 10 kilowatts, then our IC power supply with 2 kilowatts, and our oscilloscope where we will be sensing the signals. So if we take a closer look, here we have our converter that we showed before, and now the AC source is plugged in, so the converter is regulating at 12 volts, but it is switching at pulse mode. So to keep the output voltage constant to 12, but avoiding unnecessary switching losses. So if we start loading the converter, it will start switching properly and regulates the output to 12 volts. So for example, now we are delivering 30 amps, which is almost half load. And if we take a closer look, here we can see the detail of the soft switching effect, where the switch node goes negative because of the effect of the current through the parasitic diode, and then the controller turns off the MOSFET once this voltage is down. So this is the soft switching effect on the low side.
Okay, so that's all we have time for, and now we're going to move on to answer your questions in the Q&A section. Thank you very much for your attention.
Thank you, Tommy and Uriol, for your presentation. As we said, like now it's for a QA session. If you have any question, you can use the button you can find in your Zoom view and ask through there. And we will try either Uriol or Tommy or our FAEs, Florian and Nicolas, to reply. So somebody's asking about the efficiency curve of this converter. Do you have some data, Uriol?
Yes, typically we can design to fit a better efficiency about 80% of the load, but since this controller have different switching techniques depending on the load, it is almost flat. So you can have high efficiency under light load situations, but also good ones with nominal values of the inductor. And with these combo solutions, depending on the output current, but we can have efficiencies up to 93% with synchronous rectification in this case at the output.
And what is the maximum efficiency you think we can get with 12 volts and 600 watts?
Yeah, I think that the maximum efficiency we can have is around 93%.
Okay, thank So another question, it is possible to parallelize LLC converter with MPS IC?
At the moment, we have not studied this situation, but we have other with this solution. But we have other designs with other technologies, basically with digital controllers that we can study or we can try to parallelize these converters. But yes, and at the end, I've not tried it myself, but at the end, this HR 1200 family have primary side current control, so I think there would be no problem on doing such a parallelization.
Well, one of the things that could be an issue, no, it's regarding the moving frequency. No, if you really want to have kind of an interleaving to reduce the output ripple and even the input ripple could be challenging. But as Uriol pointed out, we are working on digital solutions to implement this that we expect to have new versions during 2021. But right now, this one it's more thought about standalone, but it is true we have not tested to parallelize. Any other question on how to use this tool that we have online, so you can also try it to design your converter, or any other question regarding, let's say, the functional areas? Okay. So thank you to everybody to attend. As I said before, this webinar is part of the Electronica series. We have one more. No, we have one. We have another question in the last minute. What is the maximum power is typically for LLC converters?
With half-bridge structures, we use it until up to 800, 1 kilowatt. I think it's the peak power. Over this 1 kilowatt, we need then to use full bridge structures and also take care about the thermal operation and so on. So I think that with this solution, we can go up to 1 kilowatt with the half bridge structure.
Okay, thank you. So any other question? If not, as I say, it's part of 18 webinars we're doing this week. Later on, you can have also other webinars regarding high power solutions from MPS, and also new modules we are going to have on MPQ 886 family for automotive also. So you are welcome to join. Also in the website, you have the opportunity to find our FAs connected, so you can have a direct chat with them if you want. Just go to the website, register, and then the FAs available will join to you. You can discuss technical things, maybe some product power architectures also you can discuss, and that's all. Thank you for everybody to be with us, and see you in the next webinars.
Thank you very much.
Thank you very much. Bye.